Okay, sorry about that. My son walked in at the end of that last video, so I had to cut it short, but we're just going to pick up where we left off. So we were talking about projectile motion. We know that projectile motion usually takes on this parabolic trajectory. So if you can imagine at any given point in time, t, this projectile is going to be at different positions along this path. T equals 2, t equals 3, and so on and so forth. So the x and the y coordinates of the point representing the position of this projectile can be parametrized using the parameter t, where t represents the amount of time this projectile has been in the air, essentially. So there's some quantities that we need to be paying attention to. So there is this v naught, which represents the initial velocity or speed of the projectile. And that initial velocity I can represent this way. It's going to vary depending on what it is that's launching this projectile. We also have a value theta, which is what I'm calling the angle of propulsion, or you can think of it as like the launch angle of this projectile. It's the angle that the initial trajectory of the projectile makes with the horizontal. Okay, we have g. G is a constant. You see g showing up in our parametric equations up here. G is a specific constant that's used all the time in the sciences and in physics. It's acceleration due to gravity. It can take on two different values depending on which system of measurement you're using. So if you're talking about the metric system, acceleration due to gravity is 9.8 meters per second squared. If you're using imperial units, feet and miles and things like that, it's 32 feet per second squared. And what this is it's the force due to gravity acting downward on this projectile, which causes it to accelerate toward the ground. And that acceleration is a constant, which is given by either one of these. Typically in a problem where we're using these equations, you may need to use one or the other value for g in this equation right here. And the way that you know which constant to use is based on the units that are being used in the problem. So if the problem describes your projectile and its unit of distance is given in feet, then you would be using this. If the distance is given in units of meters or something, proportional, something in that same system, kilometers, centimeters, whatever, you'd be using 9.8 meters per second squared. H is going to represent the initial height of the projectile. We've shown that here. And then t, like we said, is going to be the time elapsed since releasing the projectile. We're always going to measure time in seconds because it needs to be consistent with acceleration due to gravity, which also uses seconds here. So to give you a little intuition as to where these equations come from, let me take this initial position of our projectile and redraw it over here. So again, we have the initial velocity v naught, and this can be represented by a vector, which is something we'll talk about in 10.8, the next section. This is what we call a vector. We know that it makes an angle of theta with the horizontal, and what this does is it allows me to create this little right triangle. And I can think of this this velocity as being broken down into two components. There is a horizontal and a vertical component. So if v naught is at an angle like this, then I can use some trigonometry to solve for these sides. I'm thinking of v naught, even though it's a velocity, I'm going to interpret it as the length of this hypotenuse right here. So these values would be v naught cosine of theta and v naught sine of theta. Okay, and those are easy to derive. It's going to look very similar to how we derived our conversion formulas for polar coordinates. But what that tells me is that, imagine that this projectile we'll use an example in a minute like this, is a baseball being hit by a batter. The components of that velocity are horizontal and vertical. So the vertical velocity is made up entirely of this v naught cosine of theta. That's where we get this first equation from. So remember, the uniform motion equation from algebra says that distance is equal to the rate of speed times the time. And this is what this is saying. X is going to represent the horizontal distance that this projectile has traveled. So this would make sense to use for our equation for X. Notice Y is more complicated. And the reason for that is because the velocity acting vertically is not going to remain constant. If you struck this ball or this projectile upwards like this, it's going to have an upward velocity, but then gravity is going to be diminishing that velocity over time. It's fighting against it. And eventually, the upward velocity of that projectile is going to reach zero, and then it's going to reverse direction and come back to the ground. So this equation captures that. Now, where are we getting this from? Well, we can't give a complete derivation of this without calculus, not a good one anyway, but I can help you make sense of some of this. So, first of all, if you plug 0 in for t, that should represent the initial position of the ball. But we would want the initial position, or the initial height, since that's what y represents, to be h. That's what h represents. And you can see if I plug a 0 into this, the t squared and the t are going to cause both of these terms to go to 0, and I get y equals h. So that's why we need this plus h here. That's going to ensure that at t equals 0, we have our initial height. Now this v naught sine of theta times t, we're seeing right here. This is the initial upward velocity of this projectile. And again, distance should equal rate times time. So v naught sine of theta t will be the initial velocity. This term here, notice that there's a minus in front of it. It's negative, which means it's going to be fighting against this positive velocity here. And notice it also takes into account the acceleration due to gravity. So this term represents the effect that gravity has had on the upward velocity of this projectile at a given time t. Eventually, this term is going to overcome this term, and the projectile is going to reverse direction and start coming back towards the ground. Okay, so not a complete derivation. I didn't give an explanation as to why this t is being squared or why there's a negative 1/2 here. And again, in calculus, we can give a more complete derivation of this. But let's take a look at an example to close this section out. So this is an example from your book as well. Your book asks a few questions pertaining to this. There's only a couple of questions that I want to answer for our purposes. But it says a batter hits a baseball from a height of 3 feet above the ground with an initial velocity of 140 feet per second at an angle of 45 degrees. How high is the ball from the ground after 2 seconds? And then how long is the ball in the air? So that's 2 questions. First thing we're going to need to do is come up with parametric equations so that we can answer these questions. There's several things that we need. We need the initial velocity, v naught. That was the 140 feet per second. So 140. And I'm not going to worry about units because I'm not going to use the units in my equations. The angle, theta, that was given to us as 45 degrees. Acceleration due to gravity, remember, it can be one of 2 values. So what we do is we go and we look through the problem for any units of distance, 3 feet. I'm seeing feet as my unit of distance. Same thing here, 140 feet per second. So that means we're using imperial units, and g is equal to 32 feet per second squared. And again, I'm just going to write 32. The initial height of the projectile is given to us as 3 feet. So that's a 3. I'm not going to put anything for t because t is a variable, and if we need to plug in something for t, we'll do that after getting the equations. So according to these equations up here, I need v naught cosine of theta t. V naught is 140. Theta is 45 degrees. and that gets multiplied to t. Now I can evaluate this directly. This would equal, I know that cosine of 45 is root 2 over 2, and the 140 and the 2 would cancel a little bit, and I would end up with 70 root 2 times t. So that's going to be my equation for my x. Now how about for my y? Well, y is equal to negative 1/2 times g, which is 32, times t squared, plus v naught, that's 144, oh, sorry, 140, not 144, sine of our angle, theta, 45 degrees, plus our height, which is 3. Okay, negative 1/2 times 32 is negative 16, t squared. Sine of 45 degrees is the same as cosine of 45 degrees. They're both equal to root 2 over 2. So this will simplify the same way that this does. And again, I get 70 root 2 times t. Then I have a plus 3 here. Okay, so there's my y, there's my x. Now how do we answer these questions? Well, the first one says, how high is the ball from the ground after 2 seconds? Okay, well, in order to answer that question, height above the ground is what my y coordinate of any point here would represent. So I need to use the equation for y. If I want to find how high it is after 2 seconds, then what I'm doing is I'm plugging 2 in for t here. So y, in this case, is equal to negative 16 times 2 squared plus 70 root 2 times 2 plus 3. Okay? This comes out to approximately 137 feet. This just goes into a calculator at this point. Okay? Next thing we need to do is determine how long the ball has been in the air. Well, that's a unit of time. We want a value for t. Now, if you follow the trajectory of this ball, the ball is in the air the entire time it's on this this parabolic trajectory, and we stop the clock as soon as it hits the ground. So one way of finding the amount of time that has elapsed since this ball has been in the air is to set our y equal to 0, because that's when the height is 0, and then solve this for t. Okay, so 0 is equal to negative 16 t squared plus 70 root 2 t plus 3. Now this, you're not going to be able to factor this, of course. There's a radical in here, so not, like one of the coefficients isn't even a rational number. But you can solve this because it's a quadratic by using the quadratic formula. I'm going to trust that you know how to use the quadratic formula, since you use it a lot in algebra, so you would have seen it plenty of times by this point. But if we apply the quadratic formula to this to solve for t, you're going to get two solutions. Remember, the plus or minus in that quadratic equation, or quadratic formula, gives you two solutions a lot of the time. One of the solutions you would find comes out to a negative number. That doesn't work for this problem. Time is not going to be measured in negative seconds. That would be time that preceded the batter hitting this ball. So of the two solutions that the quadratic formula gives us, we would want to go with the positive one. Now you need a calculator to get this, but that positive root of this quadratic equation comes out to approximately 6.22 seconds. Okay. That's it for 10.7.